Hi. Today we're going to talk about the properties of covalent substances, building upon the ideas we saw in metallic and ionic substances. So for today, I actually have something to show you in person. I have here a bottle of seltzer, strawberry watermelon, so this should be pretty tasty. It says that the ingredients are just carbonated water and natural flavors. So carbonated water is carbon dioxide dissolved into the water. So if you look really closely, I'll wipe this because we're getting some condensation. You can see that there's nothing in the water, right? The liquid looks completely clear. There's nothing that you can see. So if if there's anything in here, it's dissolved. It's a homogeneous mixture. This is a solution. As we open the container, you see these little bubbles start to form. And these little bubbles are carbon dioxide gas that was dissolved in the seltzer, now undissolving and coming up to the surface. So this information tells us that carbon dioxide and water don't really mix that well as substances. Tastes good though. The question for today is why? In addition to talking about why, I think it's fair to say that looking at the properties of water and carbon dioxide, we can draw some similarities, but there's also some pretty clear differences. To take a look at the conductivity and the malleability, we already talked about the conductivity of water, but you can see that the conductivity of carbon dioxide is the same. And the malleability, I guess we need to think of the solid. Obviously, ice, if you try and bend ice, it does not bend, it breaks. And the same is true of solid carbon dioxide, also known as dry ice. And I thought it would be good to mention it here. One of the things that's kind of unique, relatively unique about carbon dioxide, is that the solid phase will transition directly from the solid to the gas without melting. So at conditions that we observe here and now, at like standard temperature and pressure conditions, liquid carbon dioxide doesn't exist. So like with water, you have ice, it will melt into liquid water and then eventually evaporate or boil if you heat it up. That doesn't happen with carbon dioxide. But what you can say is that for water, the melting point and the boiling point, way lower than the stuff we've seen for metallic and ionic substances. But carbon dioxide, well, water has these much higher. So it almost seems like within covalent substances, there's two different classifications. And again, I want to build up this idea of where these properties come from based on, the particle arrangement and the particle interactions that occur. So obviously solid covalent substances do exist, and they exist for the same reason as ionic and metallic, where we have this attraction based on charge. Charge is really everything. The difference is for a covalent substance, whether it's polar or nonpolar, the overall molecule is neutral. There might be a negative side and a positive side to each of these bonds, and there might even be a negative side and a positive side to each of these molecules, but the molecule as a whole overall is a neutral charge. So when two water particles get close to each other, the attraction is much weaker even if it is present. And then when you're looking at things like carbon dioxide that are nonpolar molecules, that attraction is even less so. So I think that would be a big differentiation point between the water and the carbon dioxide is that molecular polarity. That said, you can still get them into the solid phase where you can stack them on top of each other like you see here in this sample of CH4. But because there is that lack of strong permanent charge, the attraction is that much weaker, and that's what leads to that lower melting point. It also leads to that brittleness, because if you, again, disrupt it like you do in the case of the ionic compounds, it breaks. There is no motion here. There is no mobile particle that would allow you that malleability that you see in metals. And again, because you don't have that mobile particle, there's no full charges and there's no motion, so there's no conductivity. Obviously, in the case of sodium chloride, if we were to melt sodium chloride or turn it into the gas phase, those ions are free to move, and so that's where you get your conductivity. But again, neutral overall covalent substances, you don't see that charge moving. To really highlight the difference between polar and nonpolar molecules, I thought it would be beneficial to talk about carbon dioxide, which does not dissolve very easily into water. You can see there's still these bubbles present. But also, like, it might be worth looking at something that does dissolve in water, and something came to mind was sugar. And now that I'm looking at it, that's way too complex of a molecule, and I don't really want to spend time talking about it. So let's talk about glucose instead. Glucose is, of course, the monosaccharide that builds up half of sugar, so a lot of the same properties are observed. It's just a little bit simpler and easier to digest. So the question is, if we've got this idea where covalent substances are insulators and non-conductive, but there is this difference in that water has a much higher melting and boiling point, and I also know that there are some things that dissolve in water that are covalent, like sugar, and then there are some things like oil or carbon dioxide or wax that don't. There seems to be a subdivision of our covalent substances. So what I have in the upper right-hand corner here, this is a 3D model of glucose. We flattened out, here's your Lewis structure shown here in the middle of the page. But whether you're looking at the 3D or the flattened out one, it's pretty easy to see that there is an asymmetry in this molecule. There's plenty of these polar OH and CO bonds, but even so, like, the two halves of the molecule don't look the same. You can see here this is like jutting up out of the top, and so like there's no symmetry. There's a lot of asymmetrical distribution of this molecule. So this is a definitely polar substance in terms of the molecular polarity. As is the case with water, right? You got your horizontal symmetry, but there is definitely an oxygen side and a hydrogen side, which causes a non-zero dipole moment, which is also polar. For carbon dioxide, though, you have a lot more molecular symmetry, and so here we would say that this is a nonpolar molecule, and so that kind of like might influence and inform the properties that we saw before. It seems to me that a lot of this high melting point and that kind of those properties come from charges and charge interaction. So it would kind of make sense that a nonpolar substance like carbon dioxide has a lower melting point because there aren't charges. But additionally, we can say on top of that that there's this idea of solubility, of dissolving, where substances with similar polarity, being polar or nonpolar, will dissolve into each other, and things with opposite polarity will not. So to sum things up, this is the idea with our covalent substances. In general, they're lower melting points and boiling points. They're brittle, they're insulators, we covered all that. And within that, there are two groups, polar molecules and nonpolar molecules, where you can discuss differences in how they interact and differences in their properties. Now, when I say that polar molecules have higher melting points and nonpolar molecules have lower melting points, that is to say, on a completely, scaleless graph, we're going to say covalent substances have really, really low melting points, where you see ionic and metallic at a much higher melting point, and then within that you might see like polar and nonpolar, still well below what you'd see in terms of ionic and metallic interactions, but that polar substances do have higher melting and boiling points than nonpolar substances. Thanks for watching.